Hi, in this video we're going to look at Achievement Standard 91164 examination for 2024. That's demonstrate understanding the bonding structural properties and energy changes. Okay, so let's get started. The first question here asks us to draw a Lewis structure for two blank molecules that are given. And they're given an example in the middle of a Lewis structure that how they would like us to draw it. So let's just see if we can draw the Lewis structures for these two compounds. So the first one is nitrogen triiodide. So notice that nitrogen is in the 15th column here, the 15th group. So it has 5 valence electrons, and that iodine is in the 17th group. It has 7 valence electrons. So the first step that we do when we're going to draw the Lewis structure is we count the total number of electrons. So that's 5 plus 3 times 7 for each of the 3 iodines, and we get there are 26 electrons present. So next step here is we're going to put the atom in the middle with the 3 around the outside. The one in the middle is the nitrogen, and the reason it's the nitrogen because it has the most unbonded electrons. So we put the nitrogen in the middle and we put the 3 iodines around it. And then let's just give a bond to each of the iodines, because each of the iodines will have at least one bond. Now remember here, a bond actually represents 2 electrons that are shared between the atoms. So that's really 6 electrons we've accounted for. The next step we're going to do is we're going to make sure each of the outside electrons have allocated to them 8 electrons. So we give 8 electrons to each of the outside. Unless it's a hydrogen, we just give them 2. So let's go ahead and give these iodines 8 electrons each. That's 1 from the bond and 6 from these lone pairs. And let's do that to each iodine. And now let's count up how many electrons we've used. So we've used 8 around this iodine, 8 on the bottom iodine. So let's just show this. 8 on the left iodine, 8 on the bottom, and 8 on the right iodine. That's 24 electrons. We have 2 left, so let's give these 2 electrons around the central atom. And now let's just check, does the central atom have 8 electrons around it? Yes, it does. It's got 6 from the bonds and 2 from the lone pair. So this whole atom has been drawn correctly. What is its shape? It has 4 electron density regions around the center, so it's going to be a tetrahedral base shape, but only 3 of them are bonded, so it's going to be trigonal pyramid. Okay, let's go and see if we can do the next one. So here we have carbon disulfide. So carbon, group 14, is going to be 4 valence electrons from 1 carbon atom, and sulfur is in group 16, so there are going to be 6 plus 6, 12 electrons in total from the sulfurs. That's going to be a total of 16 electrons. Again, let's put the carbon in the middle. It has the most non-bonded electrons around it. Then we put the sulfur on each side to it, and let's give a bond between each of them. So I've used 4 of the bonds. Now I'm going to make sure each of these sulfurs, the outside atoms, have 8 allocated electrons. So they have 2 with the bond, and then they have 6 more with these non-bonding electrons, and then we have 6 more for the other sulfur. Now what we noticed here is that we've used up all of our 16 electrons. There are 8 around each sulfur atom. Let's just check the carbon to see how many it has around it. It just has 2 from the bond on the left and 2 from the bond on the right. That's 4 electrons. That's not enough. It doesn't have its allocated number of electrons, and I've used up all of my electrons. So my next final step here is I need to move 2 of these non-bonding electrons, 4, 2 from each sulfur atom, and make them share with the carbon atom. So I'm going to remove 2 electrons from the left here and make a double bond, and 2 electrons on the right and make a double bond. And if I check the atom again, we can see that each sulfur has 8 electrons around it, and the carbon has 8 electrons around it, and I've used 16 electrons in total. So this is the correct Lewis structure, and the shape here is linear. Okay, so if I was going to mark this this year, 2014, what they said is they just give you an achieved grade here if you either got 2 Lewis structures right or you got 2 of the shapes correct. So the next step here is compare and contrast the shapes and angles of silicon tetrahydride and azanone HNO. So we've got silicon with 4 hydrogens and the nitrogen with oxygen on one side, hydrogen on the other. We have to compare their shapes. Now when comparing the shapes, I have the acronym that I use, which is SARASBO, which is I need to include all of these discussion points in my paragraph. I need to say what the central atom is, how many electron density regions around the central atom. I need to state that they mutually repel each other. I need to say the angle of between the bonds. I need to talk about the base shape, how many bonding regions, and the overall shape. I need to include all of those 7 points when I'm writing each one of these paragraphs. So let's just see if I include them in my answer here. So I'm going to talk about what the shape for silicon tetrahydride is. Here I can see it has 4 electron density regions around the center, and they're all U, so I know it's going to be tetrahedral, but let's justify this explanation. So there are 4 regions around the central silicon atom. Okay, so now I've talked about electron density regions and them being around the central atom. You need to make sure you link that their position is around the central atom and state what it is. The next thing I'm going to say is that these regions repel for maximum separation, so they push away from each other as much as possible, producing angles of 109.5 for a base shape of tetrahedral. Notice here I've completed SARAS, or the first 5 of the 7 points here. So now I'm just going to talk about the bonding regions and the overall shape. All of these regions are bonding, so the overall shape is tetrahedral. Here I have included all points for my SARASBO paragraph, but remember I had to talk about both of them. So let's talk about the next one. Okay, so the next one, there are 3 electron density regions around the central nitrogen atom, repelling for maximum separation, angles of 120 degrees this time, and its base shape is trigonal planar, and only 2 of these regions are involved in bonding. The overall shape is bent. Okay, so if you can identify correctly the number of bonding or lone pairs or regions in one molecule, they'll give you an achieved. Or if you can tell me that the electron density regions are push away for maximum repulsion, that's also an achieved. Or if you can state the correct bond angles for one of them, that's an achieved point. If you can link the total number of electron density regions around the central atom to the base shape and bond angle, okay, so if you can actually say that there are 4 electron density regions around silicon, therefore it has a base shape of tetrahedral and a bond angle of tetrahedral, they'll give you a merit, okay, if you do it for one of them. Now you get an excellence if you explained bond angles, shapes of both molecules by referring to electron density, repulsion theory, and non-bonding. So if you include all of SARASBO for both, they're going to give you an excellence point. So the achieved and merit are quite straightforward if you're following this acronym here, and you should, if you're careful, be able to get the excellence grade here. Okay, so the second part of this question, hydrogen sulfide and hydrogen cyanide molecules are of different shape, but they both have the same polarity. The Lewis structure of both of these molecules is shown above, so they've drawn the Lewis structure for us, so that's great. Circle the words that best identify the polarity of both H2S and HCN. Okay, so sometimes we're not sure whether they're both polar or not polar, so what we want to do is explain the shape first and then say whether they're polar or not polar. However, in this case, if we can think about this, we can see for hydrogen cyanide that this molecule must be asymmetric. There is an H on one side, a C in the middle, and an N on the other side. Now these bonds, there are 2 distinctly different bonds. They must have 2 different dipoles. Therefore, they must be asymmetric. Because it's not asymmetric, they must be polar. Because if they're symmetric and they're 2 different bond dipoles, they're not going to pull equally, and they're going to have their dipole moments, the overall poles in different places. If they're asymmetric, well, they're not going to be polar either. So these are both, they're both going to be polar as well. So this is going to be a polar molecule, okay? So let's see if we can explain this. Now, when I want to explain about polarity, I use the acronym UBAC. Okay, now the acronym UBAC is EU, like in Europe, BAC. And the 5 things I always want to talk about is electronegativity difference between the atoms in the bond, that the atoms unevenly share the bonding electrons to produce a bond dipole. And then I talk about whether this the arrangement of the bond dipole, the polar bonds or bond dipoles are asymmetric or symmetric, and then state whether they cancel or don't cancel out. Let's have a look at this in action. Okay, so hydrogen sulfide has 2 bonds and 2 lone pairs, so the molecule shape is bent. So we're happy with that. So we know that these 2 bonds are going to be arranged asymmetrically. But we actually have to make sure we state everything. So the first thing we're going to state is that hydrogen and sulfur have a difference in electronegativity, so they share their bonding electrons unevenly, producing a bond dipole or a polar bond. Okay, it's a polar bond, but a polar bond has a bond dipole in it. Now, as it's bent, right, then the polar bonds are arranged asymmetrically. That means that the bond dipoles, not the polar bonds, be careful here, it's the bond dipoles do not cancel out and the overall molecule is polar. Okay, so that's correct. We said they were both polar, so that's a good reason. But why is the second one polar? Okay, so the second one, let's have a look at the mark here. If you stated there's electronegativity difference between H and S, that's an achieved. If you linked the asymmetry to the bond dipoles not cancelling, you're a merit here. So let's see if we can do the next part though. So hydrogen cyanide has 2 bonding regions. Yeah, we can see that. There's this triple bond and the single bond around the central carbon atom. So the molecule is actually linear. So this is a symmetrical shape, though it's not a symmetrical molecule because the atoms are different. But anyway, the difference in electronegativity between hydrogen and carbon and nitrogen are different. Okay, so they're 2 different pairs of different atoms, so they don't have the same difference in the electronegativity. So therefore, these 2 separate different bond dipoles have different strengths. That's important. And that's important whenever you talk about one of these molecules that have 2 different types of bonds in them. They'll always have different strength bond dipoles. Now, even though these bond dipoles are arranged symmetrically, because they are different strengths, the bond dipoles do not cancel out overall and the molecule is polar. So here we really need to emphasize that it's because they are 2 different bond dipoles with different strengths, they do not cancel out even though it's symmetrical. If you link the strength of the polar if you talked about the different strength of these bond dipoles, that's another merit point, right? To get the excellence here, you need to justify with reference to the electronegativity difference, the symmetry, the bond dipoles cancelling or not cancelling. You need to put everything in here to get the excellence. So basically, if you cover all of these points, you get the excellence. If you manage to say something about, hey, hydrogen and carbon, carbon and nitrogen are different bond dipoles, they have different strength, that's a merit. But if you are able to finish the whole thing, that's an excellence. One of the problems that people had when they sat this paper is they put non-polar for a start. They actually, the big hiccup here was people looked at the first Lewis structure and thought that it was just a picture of the shape. It's not. Remember, a Lewis structure is not the shape picture. So they looked at this and they said, oh, it's symmetrical, therefore that must be non-polar. And then they tried to justify hydrogen cyanide being non-polar. You need to be very careful of the terminology they hear. Because they said Lewis structure, you need to then go through and look at hydrogen sulfide and say, hey, this is a bent molecule, therefore it's asymmetric. And people who actually identified the correct shapes of both of these got the answer completely right, and those who didn't, who made that fundamental mistake, got horrible marks for this. Let's look at the next question. Okay, still the first question actually, but anyway, methanamine that's CH3NH2, is used widely in the production of pharmaceuticals, fungicides, insecticides, cleaning agents, and the fabric industry. Although hydrogen cyanide is highly poisonous, it can be used to produce methanamine as shown in the reaction below. So here's a reaction: hydrogen cyanide plus 2 hydrogens makes methanamine, and it has a heat of enthalpy of reaction on the right. Calculate the mass of methanamine formed when 1,890 kilojoules of energy is released. There's a lot of information here, but I always remember the following equation. And I just plug in the values to solve these types of questions that they're going to give me. The following equation here is Q, the total amount of energy, equals the enthalpy of reaction divided by the coefficient of the substance we're talking about from the equation, multiplied by the moles of that same substance. Now, in this case, they're talking about methanamine. So we want to work out here, what's the delta RH for the calculation, what's the coefficient for methanamine in this equation, and then what was the Q. So here we can see this is the delta RH, it's negative 158. The Q, the amount of energy released, is 1890, and the coefficient from the equation for methanamine, we can see that CH3NH2 is, there is no coefficient, so that's 1. And I'm going to substitute these 3 values into here, Q, R, and 1. Okay, and here is my substituted in equation. Now, all that I need to do now is rearrange this equation. Now, remember, if you want to rearrange an equation and you have a fraction, you just flip that fraction to the other side and turn it upside down, and that's the equation rearranged. So we get N equals 1,890 divided by 158, which is 11.96 moles. So that's how many moles were produced. Now, here, remember, it said the mass. So to find the mass when we know the moles, we're going to use this equation. The mass equals the moles times the molar mass. Now, we would assume, if we've done everything right, they should have then told us what the molar mass for methanamine is, and they did. Here it is. It's 31, so we just substitute the moles in here, 11.96 times 31, and we get 370.8 grams, or 371 grams, to 3 significant figures, because that's what they asked us at the start of the paper to write all of our answers to. Now, if you were to do this calculation correctly and get 371 grams, they will give you a merit for this. Now, if you missed one of these steps, if you got the moles correct but then substitute the other values incorrectly, you get an achieved. Or if you got the first part of the equation, if you got the, let me see this. If you got the first part correct but didn't do the second part, you'd still get the correct and achieved as well. But you have to get it all correct to get merit. Okay, so the next one is choose a correct energy diagram to represent the reaction above and label it with the information provided. So we're looking here, okay, so at this equation here. Now this equation gives us all the information we need for an energy diagram. The most important thing that we have here is we have negative 158. That means that the equation has, or the reaction has lost 158 kilojoules per mole of energy. Therefore, the graph must decrease, must get smaller. Okay, and remember, the horizontal line on the left is the reactants, horizontal line on the right is the products. So we just take the reactants and we put them on the left at the top here. We take the products, we put them down the bottom here, and then we're just going to draw an arrow and label the difference between the height, how high the products are compared to the reactants, as delta RH. That's the enthalpy or energy, and that's negative 158 kilojoules. Now, I need to, you can't just write reactants and products here because it said label it with information provided by the equation. So they want the specifics here. Choose the correct equation and label it. Now, here, if you did this correctly, got the right energy diagram, but you just put reactants and products, okay, and just put delta RH but didn't give it the value, they will give you an achieved mark here. Interesting, there's just an achieve mark for this if you did that. But actually, if you labeled this correctly and did the previous equation correctly, you get excellence. So if you made a mistake in the labeling here, you lose the opportunity to get an excellence for this part of the paper. And this was another killer for people who are sitting this paper. So make sure you put all the detail in here. You need it for an excellence. The value for delta RH is absolutely, you need that there, negative 158 on this diagram. If you'd put delta RH, which seems reasonable because look, you're just referencing over here, they would have only given you achieved here instead of the excellence that you should have got. Okay, so for this first question, we added all of our grades up. If you got 3 E's, you get an E8. If you get 2 E's, E7. If you get 4 M's, M6, 3 M's, M5, 4 A's, A4, 3 A's, A2, 2 A's, 1 A, etc. So that's the first question done. Let's go on and have a look at the next one. Okay, question 2. So question 2 is we're looking at substances. So we're looking at types of substances that we can put molecules into, or compounds into. So here we've got a table we have to complete first. It says complete the table for each substance in their solid state, and we're given 4 different substances. Now you should be familiar with these tables. This table in this case, they'll give you a merit if you do it completely correctly. So the first one we've got here is silicon dioxide. Now you need to remember that silicon dioxide or carbon by itself are the 2 types of compounds that we need to be aware of that are covalent networks. Okay, now I've put 3D covalent network. If you just put covalent network, that would have been fine. Now you also need to be able to know that the type of particle in these covalent networks is always atoms, and the attractive forces are strong covalent bonds. So you don't have to put the strength in here, but they are covalent bonds. When we get to the next compound here, the next solid, we have silicon chloride. Okay, now what we want to do is use this periodic table down the bottom here, and we want to find out where silicon is. Here it is. It's a non-metal. Okay, now remember, you'll be given a periodic table, but you won't have the staircase on there, and you always just start the staircase just above aluminium, and you draw it down so you can recognize where the non-metals and the metals are. Now, if you have a metal and in this case, a non-metal and another non-metal, if you have 2 non-metals and it's not silicon oxide or carbon, then we know it's going to be a molecular solid. And we know molecular solids are made up of molecules, right? And that these molecules are held together by weak intermolecular forces. Let's do the next one. So the next one is copper chloride. So again, let's find copper on here. It's in the metals and chloride is on the non-metals. So there is a mixture of metals and non-metals in this compound here. So we know this is going to be an ionic type of solid. Okay, so therefore it's made up of ions and it has strong ionic bonds. The last one we have here is aluminium. Now it's only one type of atom, but that's fine. But we can see that aluminium here is a metal. So it is metallic. It's made up of metal particles. But remember, if we're metals, it's metal atoms and delocalized electrons. So when we do metals, we always need to state the delocalized electrons as well. And there are metallic bonds. You need to practice and be familiar with this. This achieved and merit grade they will give with this is really important for the rest, for gaining marks in this part of the paper. So here, basically, if you got 2 rows or 2 columns correct, they give you an achieved. If you get it all correct, they give you a merit. So the next part here is both silicon dioxide and silicon chloride contain silicon, but silicon chloride has a considerably lower melting point. Explain why there is a difference in the melting point of these substances. So if we look up here, if we've done this correctly, it's a lot easier because we already have summarized the type of solid it is. We can see that silicon dioxide is a covalent network where silicon chloride is molecular. And we know that the melting point directly links to the strength of the attractions. And we have covalent bonds that are very strong and weak intermolecular forces, so that's what we're going to state it. That's the argument we're going to make here. But the first thing we have to do is we have to go over and state we have to talk about what type of solid it is, a type of particle, and attractive forces. So, silicon dioxide is a 3D covalent network made up of silicon and oxygen atoms. Okay, we've said there were atoms here, but say specifically that they are silicon and oxygen, and they're held together by strong covalent bonds. You need to make sure you talk or introduce this idea that they're strong, because you're going to use this argument, because if they're strong covalent bonds, they need a lot of energy to break them, therefore they have a high melting point. And that's going to be our next bit of writing here. We're going to link that to it. We're going to say the melting point is high because they have strong covalent bonds, and you need to break them in order to melt them, and that needs a large amount of energy. And then you just say the opposite, of course, and we're talking about silicon chloride. So silicon chloride is a molecular solid made up of discrete. Discrete means independent, away from each other, silicon chloride molecules. These molecules are held together by weak intermolecular forces of attraction. So we're using this work we've already done on the table. We're referencing, however, the strength of these attractions. And then, of course, you're just going to state the same thing that you did with our silicon dioxide, but say, well, it's a small amount of energy. A small amount of energy is required because they have weak attractions, therefore they have a lower melting point. So here, if you identified that the melting point is related to the strength achieved, or if the forces need to be broken to melt them, achieved. If you describe the structure, that is, if you said the first paragraph of each of these points here that they were exactly what you'd put in the table above, you get another achieved point. If you link the strength of the forces to the energy required for melting for one of the substances, so if you did the first part here, you get a merit. And if you did it for both, they're going to give you an excellence. Here I've just summarized and said the difference in the melting point of these substances due to the difference in the strength of their attractive forces. So yeah, we get an excellence here for, this is more a straightforward, you should be well practiced in being able to write this type of question here. Okay, we would well expect this to be in there. This is a common question and a nice way to pick up marks. Okay, so now we're going to talk about something a bit more tricky, because last time we just talked about the attractive forces and therefore the melting points. But here they want to explain why silicon tetrachloride does not dissolve in water, but copper chloride does. So this is always a more tricky explanation. We need to talk about the structure and bonding, as we did in the previous question, and the type of solvent will dissolve in and why for silicon chloride, and include a diagram with copper chloride. Well, we should have practiced drawing these diagrams, but let's see how we go. So in the first instance, the silicon chloride bonds are polar and arranged symmetrically. Therefore, the silicon chloride molecule is nonpolar. Now, we don't need to go into that detail, but if you knew that silicon chloride was nonpolar, well, good on you. That's what you should have said. Okay. Water is a polar molecule. This is really important because water is usually the one we talk about the most, with a positive hydrogen atom and a slightly negative oxygen atom, or partially positive they use here. You could say slightly instead, due to the polarity of the oxygen-hydrogen bonds. Okay, so water is a polar molecule, but silicon chloride molecule is nonpolar. Silicon chloride, being nonpolar, we'd expect it to dissolve in a nonpolar solvent, because the strength of the silicon chloride the strength of attraction between silicon chloride molecules and the attractions between the molecules and the solvent would be similar, so they can dissolve, right? So the way that it works here is, if we have two different molecules, if the strength of the attraction they have for each other is similar to the attraction they have within themselves, then they will dissolve. However, the strength of attraction forces between silicon chloride that is nonpolar and the polar water are not sufficient to overcome the strength of attraction between the water molecules. And this is maybe the most fundamental point. The reason things don't dissolve in water is not because they can't form as strong attractions with the water they have for each other. It's because the water molecules form these strong attractions to each other because they are polar. Okay, and this is the specific type of bonding is called hydrogen bonding, but silicon dioxide cannot form attractions as strong as attraction that water molecules have, two water molecules as strong as the water molecules have for each other, therefore it won't dissolve in water. Okay, so what about copper chloride? Well, copper chloride is an ionic compound. When placed in the polar water, the partial negative oxygen atom of water molecule is attracted to the positive copper. Okay, and the hydrogen atoms, the partial positive hydrogen atoms, are attracted to the negative chloride ions. The strength of this force, attraction force, between the hydrogen and oxygen parts of the water molecule to their opposite ions is strong as the attractions that the ions had for each other, so they will dissolve. So here's our water molecule with the partial charges shown, and we can draw our ion here. Here's a copper ion, and you can see that it has this attraction to the partial negative charge of the oxygen atom from water to form these attractions that are as strong as the copper had for the chloride ions. And the chloride does exactly the same with the water molecules, with the hydrogen part of the water molecules. So this is why that ions can dissolve in water, because the negative ions can form strong attractions to the positive dipole, or the positive dipole moment, the positive H, and the positive ions can form attractions to the negative dipole moment of the oxygen. Now, in this case here, you got a lot of marks for this question. If you identified silicon chloride as nonpolar and water as polar, you got achieved. Or if you identified that silicon chloride would dissolve in a nonpolar solvent, that's achieved. If you are saying that attractions are required between the water and the molecule or the solvent in the molecule, then you get achieved. If you link the strength of the attractions between the solute and solvent for one solute, so if you talked about water and said, hey, it's the strength of the attraction that the water molecules have to the ions that determines whether it dissolves in water or not, that's a merit. If you linked the polarity, or that it's to do with it being polar, or so if you said because it's non-polar it won't make strong attractions to water, you get a merit as well. Excellence if you justify the solubility of silicon chloride with reference to polarity, strength of attraction forces, and need to overcome existing forces. And you include a reason for why silicon chloride would be expected to dissolve in a non-polar solvent. This is actually quite a mess, how they marked this one here, because there was so much involved, because they talked about two different solvents. But look, if you carefully wrote down the answers here, and I knew this took up a lot of space on the paper, and you just focused on, because let's say you focus on water and you said, hey, because this has a positive charge, it will form strong attractions with water. These attractions will be as strong or stronger than the attractions that the copper had for the chloride, therefore it will dissolve. You're going to be looking at getting the excellence grade here. And you need to have some confidence and make sure you just clearly put down those arguments so that you can get these answers that will get you through. Okay, so let's just go over this one just really quickly again. Actually, there were two excellence points. So if you think about it, if you talked about the silicon chloride and its ability to dissolve in water and or non-polar solvents, that you can get an excellence grade for that if you did it all correctly. If you did the copper chloride one correctly, its ability to dissolve in water, you can get the excellence for that. The first part for the silicon chloride with the non-polar and the polar is quite it's quite a high bar to get over. But look, you should have practiced how to explain how to justify why ionic solids can dissolve in water, and you should be getting an excellence grade there if you're quite careful with your explanation. Now, for this, there was just two questions, really 2 pages of questions here about the types of solids and their properties. If you got 3 E's, which is these 2 E's here, and the E from the previous part of the question, you get an E8. If you get, 3 E's, if you got 2 E's, you get an E7. That means 1 from here, 1 from the previous question. 4 M's, you get an M6, 3 M's, M5, and then for each one of your A's down to get an achieved. Okay, let's go on and look at the last question. Okay, so question 3 here. Bottled gas supply in New Zealand is 60% propane and 40% butane. This combustion reaction for propane and butane fuels are given below. So here's the 2 equations and these 2 subsections here. Show that by calculation how much energy is released when 1 kilogram of propane compared to 1 kilogram of butane. Okay, so that's cool. So here we are given the 2 we're given 2 equations. One thing to note about this part of the paper is, and I hope it didn't upset anyone when they did it, but actually they gave the incorrect value for the amount of energy released from butane, because here they're giving 2 moles of butane compared to 1 mole for a start, and this is actually not the correct value here, but you just have to work with the value that they give you in questions like that if you find a mistake. Okay, so for the first part here, so let's see if we can work out the amount of energy. Now remember the equation we used previous, which is the Q equals delta RH over the coefficient times the moles. We're going to use that first, that equation, and we're going to work with propane. Okay, so they've given us some molar mass of propane here. So the first step could be is we're going to work out how many moles of propane we're actually working with. Now take care, this says 1.00 kilograms, which was 1,000 grams. Okay, so we have 1,000 grams, and here we have a molar mass of 44.1. We're going to put this in here, and we get how many moles? That's 22.68 moles. Okay, and remember we're using that equation, Q equals delta RH over coefficient times N. Now here we can see that the delta RH is negative 2,044, and we can see that the coefficient is 1. So we substitute that value in as well as N from down the bottom here, and we solve to find Q. And here we get negative 46,300 kilojoules. Okay, so that's cool. We've worked out how many kilojoules when we get a kilogram of propane. Let's do it with butane. So we do exactly the same with butane. Here we have the molar mass here. So we have 1,000 grams and 58.1 grams per mole. So we have 17.21 moles. The delta RH here is given, so we can, and here's the coefficient, it's 2. So we substitute those values into the equation, and we use the moles that we worked out here, and we work out that there is negative 24,800 kilojoules. Now this is where the problem, that if you knew, you knew some of these values beforehand, of you using logic, you would say, oh well, that doesn't make sense. That if you use the same amount of butane, you would produce half as much energy. It doesn't, because this is incorrect. Remember I said they gave the wrong value for this equation, but we just have to work with what there is. So this is what we get as the answer, and here we need to say how much more energy 1 kilogram of propane than 1 kilogram of butane. And of course we can say, well, 1 kilogram of propane will give you 46,000 minus 24,000, and that's 21,500 kilojoules more than propane. Okay, so this is achieved merit excellence. If you got one of these steps correct, you get achieved. If you get either part 1 or 2 correct, that's a merit. If you calculate how much more energy, I don't know how that gets you an excellence. It's not really that much harder, this minus that, then they give you the excellence. To get the excellence, you also have to have all the correct units and the correct process. Okay. So the next part here is B. The reaction of hydrogen fuel cell is shown. God, the language isn't working well today. Hydrogen reacts with oxygen to produce water. So we've got hydrogen 2H2 plus O2 gives us 2H2O. and it gives a negative 486 kilojoules per mole. Okay, cool. Use the bond energies listed in the table and the change of enthalpy provided for this reaction to calculate the average bond energy for the OH bond. Okay, so we should recognize here that what we're doing is we're doing a bond energy calculation. So I really put this down into a really simplified table. It doesn't actually have to be a table, but I put columns, and my table looks like this. I'm going to calculate the bonds broken and the bonds formed, because I know that the enthalpy, or the delta RH, equals the bonds broken minus the bonds formed. So here I'm going to look at the equation very carefully and work out exactly what bonds and how many are broken. So let's go through and do this process. So up here, the first bonds that are broken, they are hydrogen bonds from up here, okay, an H to H bond. There are 2 of them broken, and we can see here that that's 2 hydrogen bonds. So I've drawn that down here so I don't make a mistake with my arithmetic, and I can see that they are 436 kilojoules. So I'm going to write down 436. I'm going to multiply that by 2, which is 872 kilojoules of energy. Okay, so I've worked out how much energy we get from breaking the hydrogen bonds. Let's do the oxygen ones. So there is 1 oxygen molecule, that's 1 double bond oxygen. So it's a 1 O double bond O. Their energy for one of those bonds is 498, but there is 1 of them, so that's 498. That's all that's broken on the left-hand side. 2 hydrogens, 1 oxygen. So I can total up this, and I have 1370 kilojoules per mole of energy. That's how much energy it takes to break my bonds. Now we're going to work out how much energy it takes to form the bonds. Now when I look on the right-hand side, there is just 1 molecule. It's a water molecule, and if we look down here, each water molecule has 1, 2 OH bonds. Now that's really important here, and there are 2 water molecules. So there are 4 OH bonds because there are 2 water molecules that have 2 OH bonds each. Now I don't have a value for the OH bond, and the reason is because they asked me to calculate the value of the OH bond. So because I don't know this, this is going to be X. And because there are 4 of them, the total amount of energy is 4x. So I can work out the energy for forming the bonds is going to be 4x. Now this is important because now I'm going to use the equation that we can get from our resource sheet. Is the energy of the reaction, the enthalpy of the reaction, equals the total of the bonds broken minus the bonds formed. And I'm going to substitute these 2 values, 1370 and 4x, into this equation. And I get the following answer, which is negative 484 equals 1370 minus 4x. And then I rearrange this equation to make x the subject of the equation. So 4x equals 1370 plus 484. Now I did that by subtracting 4x on both sides to put it on the left. Sorry, not subtracting, adding 4x to both sides, it ends up on the left, and adding 484 to both sides, and 484 ends up on the right. So I get 4x equals 1854, and therefore x equals 1854 divided by 4, and that equals 463.5 kilojoules per mole, or the OH bond enthalpy is 464 kilojoules per mole. Okay, if I got one of these steps, if I correctly calculate 1370 or 4x, I get an achieved. If I did this whole process correctly, but with a minor error, let's say I just put a wrong value down here, I transcribed a value wrong, or let's say, and what other type of minor error there could be? Oh, that's mostly the minor errors we have here. Then I get a merit. If I get if I didn't do the units correctly, or 3 significant figures, I get a merit. If I get a correct answer with units and 3 significant figures, they give me an excellence. Let's have a look at the last question. Okay, so the last question here says, galvan is a newly developed form of carbon that is strong, light, and a good conductor. With its clean manufacturing process and wide range of applications, and anticipated that galvan could reduce the reliance on standard metals that are energy intensive to produce. As with graphite, galvan conducts electricity. What requirement must galvan have to allow it to conduct electricity? So we're going back to the properties of solids here. So the requirement of anything to be able to conduct electricity is it must have charged particles that are able to move. Free moving charged particles most likely delocalize electrons because it's similar to graphite. Now, aluminium is also a good conductor of electricity and is malleable, can be pressed into shape. These properties enable it to be used extensively for overhead power lines and for components in shelves of smartphones and laptops. Explain why aluminium has these properties and link it to the uses stated. Okay, conducts electricity. Why does it have this property? Well, because again we're talking about the structure and properties of solids here. Remember we need to say what type of substance it is, the type of particles that are involved, and we need to talk about the type of bonding involved. So let's get that out of the way first. So it's a metallic solid made up of metal atoms with delocalized valence electrons held together by non-directional strong metallic bonds. Cool. That is going to be an achieved point just in itself. We have stated the properties, so not the particles, the bonding, and the type of substance, and we get that out of the way first. Now, why does it conduct electricity? Well, these delocalized electrons have a charge and are free to move, so they can conduct electricity. Straightforward. This should be a merit point. Well done. Now, therefore, it's a good choice for overhead power lines because it can conduct electricity. Now, we need to make sure that we link what they've asked us to the context. And here they said it was about overhead power lines. Why is aluminium used for it? Because it is able to conduct electricity. That's why you can use it for power lines. Okay, so see how these three ideas link to each other. They are needed for you to get a good mark here. Anyway, so let's go to the next bit. Why is it malleable? Okay, so again, we could start off with this aluminium is a metallic solid made up of metal atoms, blah, blah, blah. I've changed it a bit because I've already said this, but really it has these strong non-directional attractions between the nuclei of aluminium and the delocalized electrons. Now, when a force is applied, the atoms move, new bonds strengthen, while the old ones diminish. So it makes new bonds while old ones get less, right? So that's really what's important here. Now, this enables aluminium to be reshaped under force without breaking or damaging the structure. Hence, it's malleable. Now, why is this important? Because you have to be able to stretch it into wires. Wait. So here we could say, well, this is important because if you want to make wires to conduct electricity, but we can also say, hey, this is really good because when you put it on the outside of your phone or your laptop, if you accidentally hit it with something, it's not going to fracture, it just might dent a little. Okay, so that's really important. So here, if you link malleability to non-directional metallic bonds, allowing the particles to move without breaking, and that's what this strengthening these bonds while they get weak, that's what it explains. If you comprehensively explained both conductivity of malleability to the suitability for the uses, that is, if you put the linked context at the end, then you can get the excellence grade here. And that here is the end of the questions in the paper. Now, if you got 3 E's here, okay, so we're looking back in these last two questions, then you're an E8, 2 E's E7, 3 M's M6, 2 M's M5, and then 4, 3, 2, 1 for the A4 down to N1. Now, the cut-offs here for the whole paper were, if you got 8 to 13, you got achieved, 14 to 18 merit, and 19 to 24 is excellence. That's pretty standard for a paper. Now, this paper was quite heavy on structure and structures of solids here, structure and properties of solids. It's not always that heavy on these, but make sure you actually practice writing out these paragraphs. And in this one, they talked about the conductivity, the malleability. Well, that's these two here. They talked about the melting points, and they talked about solubility, and those are the 4 most common ones that I would say there. and make sure that you learn about those four. I mean, sometimes they do talk about why things are brittle, and you should learn that idea as well as the malleability one. Well, I hope that's helped. And if you need any other help with these, going over these papers, look for my previous year's videos and for videos on other standards. Hey, thanks for watching this video. Hopefully this has made you more confident with your chemistry. Don't forget to like, subscribe, or leave a comment about anything that you want to with this video or any questions you have. I'll see you later.